Hi there, summer session students, and welcome to our very first lesson video on numbers, radicals, and exponents. So I'd like for you to print out the pages that we will be using, but if you want to save some ink and some paper as well, I will be printing it out for you, and you can just transfer the work that you have there later. So for now, maybe you can follow along and write notes in your notebook. And I will be checking those notes in your notebook when you get to school during your cohort schedule. So it's either going to be Monday or Tuesday. So our very first lesson would be very quick. It will be on lesson 1 on number sets. So how the numbers evolved from the time of its conception up to the numbers that we are using in math right now is what we're going to be discussing here. So it all boils down to this little diagram that I have here. I will be using a program called Algebra in Motion. It will be similar to what information you will be needing for this section here. So you can just follow along and try to write down as much notes as you can. So our very first numbers are called the natural number, or also known as the counting number. The symbol for this number is N. And people of long time ago, they own sheep, oxen, or animals, or maybe even trees, and they have the urge to count it so that they can take ownership of those particular property that they have. So they need to learn some method of counting. And the numbers that we obviously use to count are numbers 1, 2, 3, 4. Now, 1 doesn't look like one the way 1 we see it now. It evolved obviously from the different numeration system, and now this one is what we call the Indo-Arabic numeration system, where 1 looks like 1 right now. So the very first set of numbers that evolved are the counting numbers, where we refer to them as obviously natural numbers, and those are the numbers 1, 2, 3, 4, and 5. And then obviously people started asking, okay, how many sheep do you have? Well, I don't have any sheep, so I will now be introducing the number 0. So with the addition of 0, 0 joined all those counting numbers and they all became whole numbers. The symbol for whole numbers is W. So 0, 1, 2, 3, 4 now belongs to the whole numbers. And then we moved on to, what if I want to represent something that is beyond 0? For example, if 0 degrees Celsius is the freezing point of water, or the freezing temperature for water, how do we represent below freezing? So now they started to introduce the concept of integers, which are 0, 1, 2, 3, and all the negative equivalents of those positive numbers. So now our number space became a little bit bigger, and now they went into what we call integers. So now integers introduced all these negative numbers. So now the integers is the entire set of numbers, all the negative numbers, 0, and all the positive numbers. The symbol for integers is actually the letter Z or Z, which stands for Zahlen, which is the German name for numbers. I'm going to try to put that all together in your notes there. And then, so we have things that represent below 0. What about if I want to just get a portion of that particular whole? And now it gives rise to rational numbers. So any number that can be written as A over B, or it's called rational because from the root word means ratio. From the root word ratio means it's a relationship of two quantities, where A and B there are integers and B cannot be 0. Well, why can't B not equal to 0? Because we cannot divide by 0, so it will be an undefined expression. So now it gives rise to numbers like 1/4, 2/3. Let's look at some examples here and see. Like 2/3 is a rational number, so that's clearly a number that can be written as a ratio between A to B. What about -17/7? Yes. What about 2 and 7/9? That's absolutely an example. Here, -1.6 repeating. Well, first of all, that's not written as a ratio of two numbers. But if you are familiar with 0.6 repeating, 0.6 repeating is actually an equivalent decimal to the number 2/3. So maybe we'll show that not on the snipping tool, but maybe we'll show that in my highly powered graphing calculator here. That's going to show up in a little bit. So 2 divided by 3, which is a number that can be written as A/B. If we're going to write that down, that's actually 0.6666 repeating. It just gives you the number 7 at the end here because it rounds it up to the nearest last number that it can accommodate. So -1.666 repeating, although it doesn't explicitly say A/B, but you can convert that into an expression A/B. Now, is 8 a rational number? Can we express 8 as an expression A/B? Absolutely, we can just say 8 is the same as 8/1. So whole numbers are also rational numbers. What about 0? Well, 0 can be written as 0/2 or 0/5. So 0 is also a rational number. 4.2, absolutely. It's like 4 and 2 out of 10 or 4 and 2/10. Pi is not an example of a rational number. That is actually what we refer to as irrational number. Pi is an example of a number where it cannot be written in the form A/B. So what are other examples of irrational numbers? If you write square root of 2, let me pull up my highly powered calculator here again. Second, and then square root symbol here and 2. Pi here seem to really stop after 2, but if we're actually using a highly powered calculator, your 2 there doesn't end towards any particular number. It continues on and on. So in this case, any roots of non-perfect root, we're going to be talking about what is a non-perfect root later when we go to the next lesson, is considered to be an irrational number. So anything that cannot be written in the form A/B is an irrational number. Square root of 5 is the same. Pi is the same. A negative root of 99 is also the same. Cube root of 15 is also the same. Fourth root of 40 is also the same. What about square root of 25? So we're going to learn about square roots in the next section. But if we write square root of 25, the answer is actually, let's put that down here. I'm sure you are familiar with what square root of 25 is, but I'm just going to write it down in your calculator here. Square root of 25 is equal to 5. So 5 is obviously a number that can be written as A/B, which is the same as 5/1. So square root of 25 is actually a rational number, not an irrational number. So it doesn't belong to this group. Okay, it belongs to the rational number. Now, I forgot to tell you what's the symbol for rational number. The symbol for rational number is actually Q, the letter Q. And so again, why is it Q? Q is actually derived from an Italian word quotente. I don't know if I said it correctly, which means quotient. As we know, quotient is the result of dividing two numbers. So as we can see, A/B means here A divided by B. So it's also a quotient. Irrational numbers is just a Q with a little line on top, which means it's not rational. So any number that cannot be written as an expression A over B is considered to be an irrational number. And what is a real number? All these numbers that we use in our numeration system and our daily dealings in math is actually a number that is set to be a real number. You could probably ask me, so if Miss Galita, if there are real numbers, are there imaginary numbers? Absolutely. There are imaginary numbers. We don't usually use it in any of the problems that we will be using, but if you're pursuing a career in math, maybe a computer science, you're actually going to meet some imaginary numbers. The unit for imaginary numbers is the letter I, and its basic unit is basically equal to square root of -1. So if you're keen in math and you're going to be doing some higher mathematics in later in your career or in your post-secondary, you're going to be talking about real numbers. I mean imaginary numbers. If you were not able to follow along a while ago when we had that Algebra in Motion app there that I showed you, here should be a quick notes for your little introduction there. Okay, so you can copy it down quickly. Just want to emphasize that our diagram here says that all the numbers that can be written as A over B are called rational numbers, so they belong to this group here. All the numbers that cannot be written as A over B is an irrational number here. There should be no other numbers that exist in between there. And all these yellow and blue highlighted there are considered to be real numbers. And outside of the real numbers, there's also a world of imaginary numbers. So just one example here. When we talk about the number -2. So -2 is actually an integer since it belongs to your big rectangle here for integers, so it's right here. So it's an integer, but also it's a rational number and it's also a real number. Okay, so since your bigger circle Q here, Z is inside that bigger circle, then we can say that all the elements inside the bigger bigger rectangle Q is also a subset of that. Okay, so what I meant by that is Z is an inner part of the bigger rectangle Q, which means all of Z becomes part of Q. So we can say that -2 is an integer, a rational number, and a real number. Okay, so we're going to try to practice that in the next section here. Okay, so for example, example D here, where is 7 found? 7 is actually found as a natural number, so 7 is right here. So 7 is in the very inner circle, so 7 is actually a natural number. It's also a whole number because 7 is part of this bigger circle here, which is a whole number. And this whole number, I keep saying circle. So when I say circle, that means a rectangle there. Sorry, I'm not watching my shapes there. So that's a whole number, and the next one is integer, and the next one is rational number, and the big rectangle here, the big set here is your real number. So 7 is in the inner part here, which means it is part of the outer rectangle, which is a whole number, which is part of the outer rectangle, which is an integer, which is a part of an outer rectangle, which is a rational number, and then obviously a part of the bigger rectangle, which is your real number. Okay, so let's do one more thing. Let's have 4.93. Well, 4.93 is actually the same as 4 and 93 over 100. So it's not a whole number. I mean, it's not a natural number. It's not a whole number. Is it an integer? Not an integer, but it's actually a rational number. So it's 4 and 93 over 4 and 93 over 100. So it's part of this bigger rectangle here, which is your Q. It's a rational number, and it's part of your bigger real number system, which is in this case your real number. Okay. We're not going to deal with that. It's just part of the history of number systems, but I'd like for you to obviously kind of appreciate where the numbers evolve from counting to all the way to the whole real number system that we have right now. So that's our first section there. So I'm going to skip example 2. I'd like for you to do example 2 for homework. Let's have a few examples for example 3. You may use a calculator for this. So anytime a number becomes an expression in the form a over b, or can be written as a over b, then it's a rational number. Anytime it doesn't end and continues to repeat, or it's a square root, a cube root of a non-perfect number, then we say it's an irrational number. Or, excuse me, neither. So for example, if we use our calculator, we take square root of 49. The answer to this one is actually equal to 7. And 7 can be written down as 7 over 1, which in this case, it's an irrational number. So, it's a rational number. So I'm going to write that down as Q. So the symbol for irrational is Q with a little line on top. I want to rewrite that. And the symbol for rational is just Q. If it's neither, then we can just write it as neither. So I'd like for you to do this for your homework as well, example 3, and also attempt to do some of example number 4. Actually, we'll skip example 4 for your homework. All right. That's it for our very first lesson, which is your number sets there. We will proceed with the next video lesson on for your second lesson for today.